Resource reclaiming. You have some memory why we are doing this. This is in preparation for the next chapter, where we will be talking about increasing reliability. This is a small step towards doing that, namely managing your resources so that whenever they are not actually utilized, you can get them back, so that you can have more fallback positions, you can handle more exceptions, you can fill in more graceful degradation execution if you have that available. A few obvious things. Your reclaiming and all the other tools which you add on top of that are scrutinized the same way as the rest of your real-time system, so it has to be correct. Right? That makes sense. Inexpensive, so if your resource reclaiming is a gigabyte operating system kind of daemon in the background, that doesn't make any sense. Complexity have to be bound, and overall there has to be some effect of it. Resource claiming has to be leading into something which will actually increase your reliability. So in order to do that, we have to introduce a few more terms in our tasking model. It makes our tasking model now a bit more complicated. We'll also discuss multi-CPU scheduling now, which we have not been doing so far. Cycle time, we have a ready time. This is the time when the task can be scheduled. Deadline, worst case computation time. Now we have the actual computation time, obviously, because we want to reclaim something, we need to know how long it actually took. Worst case response time is obvious, and then we have a number of, we have two sets which are expressing mutual exclusion conflicts and precedence conflicts. That you know that something always has to be completed before something else starts, or they're mutually exclusive. A few more assumptions. We have now a bunch of processes available. We assume that tasks cannot migrate once they start on a CPU line. In general computation, that's not true. In real-time systems, that often is true, because you actually also associate specific pieces of resources to this CPU line. You programmed your timer to be waking up this specific core, for example, and you cannot just randomly migrate your task to another core after you have set up the whole hardware environment. So usually you assume in real-time environments you cannot randomly swap CPUs. Can you swap CPUs in your laptop with a running task after you started the task? Can you swap to another CPU? Yes?
In fact, it's hard to stop it from doing
Yes. So in fact you can do that, and you also know why it's done in the laptop, because it's just so jittery and they cannot just hold still and keeping it on one CPU. Why are they swapping it constantly? Yeah, heat distribution, that not one side of your CPU is bubbling up and the other one is freezing over. Can you plug in new CPUs while your operating system is running?
I believe that is possible.
Yeah. Your operating system is not able to do that, but it is possible to implement that nicely. Found it quite cool to see in, what was the name of this operating? BOS. Exactly. It's been doing that.
With, I mean, you can now do hot swappable graphics cards. Into something. Yeah, for example, and like they are effectively processing unit. They might be CPU.
Yeah, but for graphics card that was the case for a long time now, because we have so many computers which have multiple graphics cards on different performance levels, and for power consumption reasons, the higher performance graphics cards are usually completely powered down. And so you actually physically hit the switch to power this thing up, and then migrating the CPU workload, the GPU workload to a completely new hardware environment. So that's quite common. But your current operating system is not doing the same trick by actually powering down cores and repowering up cores. But this can be done the same way. So what else do we have? It was one task per processor. Okay, goes without saying. Task queues are in shared memory. Tasks are not preempted at the moment. So, few more terms. We have a feasible schedule, which we will also call the pre-run schedule. A feasible schedule means that at compile time, you calculated that all of your real-time tasks can be scheduled. Your schedule is feasible. We call this the pre-run schedule because we do this at compile time, not at runtime. Then you have a post-run schedule. This is the same thing in the first instance now. And the first instance is basically the pre-run schedule with the actual computation times. So you schedule everything according to the pre-run schedule, and we see how long they actually executed, because the pre-run schedule is based on the worst case computation times. That doesn't always need to be the case. We also have start and finish times, ST and FT. And we have then the actual start and the actual finishing times, a bit hard to read, with a prime attached to that. This is what happens at runtime. A correct post-run schedule, that means for all of our tasks, the actual starting times are equal or earlier than the pre-run starting times. And the more important part is that all the finishing times are in the post-run schedule before the deadline. In the pre-run schedule, they were before the deadline because we scheduled so. But in the post-run schedule, that need to be set. Why isn't the first thing not sufficient? If I set the first thing that all starting times are at the same time or earlier than our planned starting times, isn't that logically sufficient to guarantee feasibility of our schedule?
Do we have the assumption that a task can not exceed its worst case computation time?
Yes, we do.
It needs to wait for another task.
If it needs to wait for another task, what would that do? Okay.
Something starts earlier, is the deadline necessarily in the same spot?
No, we are thinking in the wrong direction. We have to look in practical cases. So what can we do in terms of resource claiming algorithms? There's the null algorithm, dispatching according to the pre-run schedule. This is similar to rigid scheduling. You're ignoring any runtime behaviors completely. And the other extreme you can do every time that a task finishes, you go back to the beginning and reschedule everything from scratch. That's a bit expensive. Usually not doing that. And optimal scheduling for tasks which are dynamically arriving and you cannot preempt them, that's an NP-hard problem. So what you want is you want algorithms without parsing, define this in a moment, which should have a constant complexity, and algorithms which pass with parsing with O log n. Beyond that, you're usually not considering reclaiming algorithms. I will tell you what parsing is on a practical example rather than in abstract terms. So this is our pre-run schedule, all nice and cool. This is how we plan to run the whole thing. Here I give you a bunch of deadlines to the whole thing. And if you look closely, all the finishing times of our tasks are before their deadlines. Pre-run schedule is feasible. Cool. All easy. Post-run schedule. Difference between pre-run schedule and post-run schedule is just shorter execution times. But we kept all the start times on the same spot. Does that violate schedulability? No, obviously not. Nothing bad happens there. We keep all them on the same spot. You're not convinced?
But why does the start time have to be less than pre-planned start time?
It doesn't have to. No, it does have to if you want to have some defined outside reaction, if the start time had a meaning in the original schedule. Okay. You could have not only the deadline associated with the task, you could also have early responses associated with the task, and for that the start time is relevant to have a look at it. Now, all of my tasks are independent. What can I do to reclaim resources here?
I don't understand what you mean by reclaim resources.
Reclaim resources, I mean using those resources, namely the CPU time, which is idling at the moment, using this idling time to do stuff. Can I use these idling slots here to just execute these tasks which are waiting at the moment?
You can have such a way in which the tasks are to be scheduled no earlier than.
Yes, assume I don't have them at the moment.
Then it could be a dangerous operation to schedule them earlier.
Yes, if I have that,
Oh.
but I'm assuming I don't have that at the moment. I don't have any constraints of you're not allowed to schedule earlier then. So they can all be scheduled earlier. It's fine. Okay. So to make that a little less complicated, I just do that. Because this is a kindergarten example, tasks are independent. In real life, tasks are not independent. Okay, so let's introduce a little bit more spice in the system. And I now claim that a few of these tasks are mutually exclusive. They have some relation to each other. So 4 and 7 cannot run at the same time. Fine. 4 and 9 cannot run at the same time. It's okay. 7 and 9, they're on the same CPU anyway, so they're mutually exclusive. 7 and 12, fine, and 9 and 12. Where is 9? 9 and 12. Okay. So in my pre-run schedule, all of these exclusions are fine. Nothing bad is happening. So far. And at this point in time, something nasty happens. Namely that the moment I'm pulling task 12 earlier, what happens to the rest of the system? Task 12 is happy. Task 12 will make their deadline, its deadline. But we have a constraint with 7. Right? So previously this was all fine because task 12 was not supposed to be started after 7 completes.
Well, what's going to happen is if you push 12 back to that position, T7 is going to have to start later because they can't play at the same time. But if T7 starts later, it's going to miss its own deadline.
Exactly. So the simple strategy, if you have a real-world system, of just starting stuff earlier because you can, is a dangerous concept. And this is called parsing in a multi-CPU system, that you have tasks completely passing in relation to the pre-run schedule, and then as a trickle-on effect from that, you're pushing other dependent tasks backwards. That's bad. Okay? And here we have 2 tasks now failing their deadline because task 12 was a bit over-eager and was jumping on an empty idling resource. So, not too great. Okay. Pushing that back. Okay, how can we do that a little more cleverly? That's our post-run schedule. Can you give me, start with a simple most idea? can you give me a simple rescheduling strategy which is not violating any of these constraints?
If you have a task which is unconstrained,
Yeah.
if its worst case runtime is small enough to fit in a gap in the schedule, bring it back.
Okay. So whenever I have the possibility to move a task which is not constrained, and I'm not touching the rest of the schedule in the process, I do it. Okay? What else can you suggest? What else can you observe?
Only reschedule a task earlier enough so that you don't change the ordering between.
Yeah, that's a general idea, but how do you guarantee that? Because this is exactly what you want. Express this algorithmically. You say you don't want to schedule anything earlier. If it does, it will do anything bad. How do you make sure nothing bad happens in the post effect a few schedules later?
Surely you don't change the order of the tasks.
If I never change the order of the task, that's a good point. So if I'm just not allowing any kind of passing, that's a good point. Now, the most trivial observation which you can have in those kind of environments is if all of your CPU lines are idling at the same time, you can just cut out this whole area of your schedule, and it's bleedingly obvious that nothing is changing to the overall integrity of your schedule if you just skip over those time frames when everybody was idling. Yeah? This is the most simple resource reclaiming scheme you can have. Your whole system is idling. Then just skip all the way to this next non-idle phase. How do you do that? Stop. And simultaneous idling, it's easy to prove that this will still lead to a feasible schedule. Okay, now to your idea. You said you're only allowing tasks to be put forward if they're not changing the overall order. Okay, now we have to define what it means to change the overall order. And for that, we're categorizing three different groups with relation to your task. We are talking about the group of tasks which are supposed to finish before you start. And I put this all into the big set of tasks which is supposed to happen before me. I'm not touching that. I'm not penetrating that territory. Then I have the group of tasks which are supposed to start after I finish. Same thing. I just leave them alone and not shift anything. And then I have the group of tasks which are already overlapping with me. Now, if the task is already overlapping with me, I can feel free to shift further. They already have been overlapping, so those kind of mutual exclusion effects which are trickling on from that one could not have been triggering any bad results, so I treat them separately. Calculating that, by the way, is quadratic complexity with the number of processors, but the number of processors is bound and small, so for practical purposes that's still a constant, even though it's technically quadratic with the number of processors, but you don't have 10,000 processors in your system, so that's not an issue. So with this basic reclaiming, what can we do there? I'm just shifting the overlapping tasks to be more overlapping. But I'm never allowing tasks to go outside the range of penetrating the tasks which are finishing before me or starting after me. Okay, that's not too bad. For anything else, we have to look a little bit closer. This is where restriction vectors are coming into play. What do these restriction vectors explain? These restriction vectors basically give you stop signs for every task where you have to be careful. When are you not yet allowed to be scheduled? And you make this dependent on the dependencies of the tasks around you. If you have any restriction with respect to another task, which means you have either a precedence relation with another task or you have a mutual exclusion relation with another task, it doesn't matter in that context. You are constrained with respect to this other task. If that's the case, you have two possibilities how to get an entry in your restriction vector. You have a restriction vector for every CPU in your system. You have a restriction entry for every CPU in your system. And this gives you an efficient information, efficient data structure to find out what is the one task I have to keep an eye on, the one task I'm not allowed to overtake. And this is done recursively so that the task which I'm staring at is itself staring at another task which it is not allowed to overtake. That way, all of the tasks maximally have to stare at the number of tasks which are the number of processors in your system. For every processor, there's only one task I have to be aware of, not to shift over that limit. To calculate that, on the same CPU, this is pretty trivial. On the same CPU, it is simply the task which is coming before me. At the moment, we are not yet allowing that we are swapping between CPUs. If we are not doing that, then obviously I'm dependent on the task which is directly in front of me. And for all the other tasks, for all the other processors, it is the closest task on another processor line which has some restriction to myself. And what the rest of that stuff says is that there is no other task in between this task and myself which has constraints with me. So this is expressing that's the closest one which is constrained with respect to me. To write an algorithm about this, I also have a completion bit matrix which basically says that this task is already done. If it's done, I can ignore it and I can start because I'm not overtaking this anymore, it's already done. So, computing the restriction vectors, I can do this at compile time. In other words, doesn't cost me anything. It's a static piece of information. And what I do at runtime, I can now, for all tasks which are scheduled on a specific processor, have a look at the completion bit matrix. This is just a global data structure which tells me which tasks are already terminated. And I start all those tasks for which I don't find an entry in the restriction vector which would stop me from doing so. Let's do this a bit more in practice. It's easier to look at that in that sense. So, make it a bit more interesting. A few more constraints added to the whole system. We have some mutual exclusion, and some of the tasks have to be happening before the other task completes. This is a static translation from all the constraints which you have seen into the local restriction vectors. Much nicer. And this can be evaluated by your online scheduler and resource reclaiming scheme at very low computational costs because that has been pre-calculated already. All these dependencies are in here. What does that mean? For example, look at the very last one. Our restriction vector for task number 13. On the same CPU, my task number 13 is of course dependent on task number 12 because that's the task which is to be scheduled right before that. But it is also dependent on task number 8. Let's just check how that came along. Yep. Task number 13 has to be coming always after task number 8. On the same CPU line, this is always quite simple, that the previous task on the same CPU line will turn up on this entry for the same CPU line. These 3 rows here are actually the 3 CPU lines, if you look closely. And there are only a few more constraints which are coming in from the rest of it. The rest is transitive, and I don't have to care about the rest of the dependencies. So, what does that do? This is the post-run schedule. And if I now allow for resource reclaiming based on the restriction vector, that's a lot denser than what we have achieved so far. What can I do? I can actually allow some limited forms of parsing. Task 11, for example, you see is moving a lot further forward. Could I do that? Where is task 11? Here. Task 11 is only dependent on task 10. It doesn't influence and depend on anything else. So I can immediately kick that thing off. Okay. Did I talk you into believing this is correct? Sort of. Before I threaten you with big equations, you rather say it's obvious. Don't have to come with that. But we should look into what is the critical point in a more formal way, which can go bad. For that, we set up a lemma which basically says that any feasible pre-run schedule. If you have a feasible pre-run schedule and we have any task where the starting time is delayed, parsing must have occurred. There's no other possibility how a task can be delayed other than a passing task in our multi-core environment. That one task must have overtaken somebody else and then pushed one task back. So this must have happened, otherwise you would not have seen starting times delayed. So is that true? We just try to negate that. Assume that no parsing ever occurred. That means that all tasks in the before me set will be scheduled before me. All tasks in the after set will be dispatched after me, because there wasn't any parsing. And all the tasks which are in the concurrent set with me do not interfere with me, which means I can randomly shuffle them around, because they don't interfere to start with. But they won't interfere if I shift them any further. And that means there could not possibly have been any delay in starting times if there was no parsing. Okay, so we have to look at the parsing cases, because the resource the resource vector reclaiming scheme does allow for parsing. Now we have to check what form of parsing happened here. So we only have to look at those parsing cases. The first one is if they do have precedence conflicts or resource mutual exclusion conflicts, then this has been transitively or immediately expressed in the restriction vector, and the resource vector algorithm would therefore have stopped that from happening. The restriction vector exactly gives you the hard stop. You can forward it as much as you want. Until that point, this is the limit. And this limit is exactly defined where you would have that form of parsing, where you overlap with tasks which have dependencies with you. So the resource vector will stop that. If it doesn't have any precedence or mutual exclusion conflicts with you, it would not turn up as a restriction vector, and you would be able to pass that task. But if that's the case, if it doesn't have any dependencies with you, and you pass it, nothing happens. Okay. A little bit more convincing? Okay. You give in before I come with even larger equations? Okay. Let's make this more interesting. What's the next stage? Let's go back to, sorry, where's my, this is the post-run schedule. This is how far we are at the moment. Can I optimize beyond that point? Do you have any idea how to utilize the remaining CPU time, which is now idling somewhere uselessly? Can I reclaim that? No way?
Probably start scheduling future tasks that popped up while this has been based on the CPU time for a while, so I work in the scheduler. And this blocks, the CPU's not doing anything.
So coming a little bit back to Nick's idea, if there is something way far in the future and it's completely independent of what I'm doing here, I'm just stuffing it into that kind of gap.
Well, like, I guess we could start pre-scheduling for the next run. Like once all three processes have stopped, and then meet them at their deadlines, and this schedule is finished.
Can they allow us what processes between cores?
Sure.
Could that be used for process?
How?
Well, in this case, it's not immediately obvious that it can be done, but I don't look for those mechanisms and say, oh, you can
Okay. Let's make it obvious. Now at time step 8, what can I schedule there at time step 8? Not 12. No? 12 is restricted. 12 is dependent on 3, 7, and 11. I can schedule 3. No, 3 is already being scheduled. I don't have to schedule it twice. 3 is already running. I can schedule 7. Is that okay?
It's blocked by its dependencies.
7 is blocked by 6. Yeah? But only because I added to the restriction vector at the moment that everything which is scheduled on the same CPU line is dependent on what came immediately before it on the same CPU line. That was dumb. No? Do I need this restriction? What happens if I kick that out? Let me have a look at what is 7 actually dependent on? What is 7 actually dependent on? 7 is mutually exclusive with 9 and 4. Do I touch anything with 9? Not for a long time. You know it all by heart already, right? You see it all in front of you. So where were we? So 7 was dependent on 9, which is harmless. 7 was only dependent on 4. It's also quite some bit in the future. And on 12. So yes, 7 could actually be run. Now how to formulate that? That we want to run 7.
You just change to just consider those sort of blocking hash and they should be just drop the restriction
Uh-huh.
on this.
Okay. Can I do this under all circumstances? If I just drop the local constraints, I will come to something like this. I'm looking at the lower equation now, not in the middle one. The middle one was the one which you already made friends with. The lower one is the same thing, only I leave out exactly what you said. I leave out the constraint of the same CPU line. I'm only looking at actual precedence or mutually exclusive conditions. Okay, so I have these. Can I now use this restriction vector scrupulously to calculate the new ones? Lot sparser. Basically nothing left. Few entries which we still have to worry about, but a very, very small number. So let's run this. This was our pre-run schedule. Let's keep that in mind. I'll just grade this a little bit. And now we go through the post-run schedule slowly. We go through the post-run schedule until now time step 8. And you want to run task 7. To do this effectively, we said that all the task queues are in shared memory anyway. To do this effectively, what you're doing, because we are not bound to CPUs anymore, what we're doing is we're just swapping two queues completely. Just assuming that this queue is no longer for CPU 2, but now this queue is actually for CPU 3. I'll just swap two of them. If we do that, plop, done. The world looks a lot friendlier. Because now I can execute task 7 without any further worries. Okay, let's do that. Task 7 is not constrained at this point. I can execute that one, which gets me to task time step 10. Time step 10, I again have empty idling resources. What can I do next? Say again?
Put 13 in the third thread.
That means I just undo what I just did before. I just swap them back. If I swap the CPU lines, the CPU queues back, I can now execute task 8, which gets me to time point 16. You see where this is going. And I swap them back again. And I think we're done. Because we actually reclaimed everything which could possibly have been reclaimed there. There's no idling left at all. Okay. Does this always work? Probably not. Is it legal what we have been doing here so blindly? Every time you're stopped, You're just looking at neighboring CPU lines, and you swap with neighboring CPU lines to get one of these tasks active. Is that always okay? Can you construct a case where this is bad? You want to swap them so that, what do we want to run? We want to run task 13, right? Is that okay to run task 13 under all circumstances here? Could you construct a case where this is fatal?
If 13 was dependent on 12, then swapping would be not okay.
Sure, but this would be expressed in our restriction vectors. It would be explicitly constrained with that. So that would have been covered by the restriction vector algorithm if that would be the case. Anything which is actually not covered by the restriction vectors, which are introduced artificially now by swapping CPU lines. That's my question. Are you sure we're still fine?
Well, this might already be expressed, but you're pushing the start time further back. Like it might mean a time that it has to pass before it can start.
Task 9 is the one I should be worried about. Because if task 9, say, would have been originally scheduled at time 18, right? Task 9 was supposed to be scheduled here at time point 18. And now I'm trying to recover these idle times by swapping the CPU line. What happens? Now you see where this is going, right? Now you see that in that specific case, task 9 would actually be pushed back because it's now migrating to a CPU line which has a longer remaining task execution time still ahead of it. It was looking forward to be executed on processor 2 well in time, even though there were a few idling elements in between, but it was supposed to be run at time 18. And now that I swapped the cores, this will be pushed back. That's the criterion which you have to be having in mind right before you swap CPU lines. And that's expressed here again, quite carefully. Namely that you're only allowed to do that if I have two tasks which I have my eye on. One task is next to be scheduled, but it cannot be run at the moment. This was our task 9. Task 9 was currently blocked because it has dependencies with something else. But it was, other than that, next in line. Would have been scheduled after this dependency is resolved. Then I can schedule that one. And I have a task which is currently executing on my processor. Now I have to make sure by swapping these CPU lines that the start time of the task which is currently blocked is not pushed back by the finishing time of the task which is currently running. That was the constraint. Okay? And if that's the case, I can happily start reclaiming and swapping CPU lines at runtime. Good. So, having a look back at all the resource reclaiming possibilities, when does it make sense to do resource reclaiming? There are a few things to look at. Task graph density. How much interdependence do I have between my tasks? If my task set is loosely dependent, resource reclaiming will have a significant effect. If my task graph is, so to speak, fully connected. Everything depends on everything else anyway, and I'm completely in a gigantic mesh of dependencies in my pre-run schedule, then your chances are your post-run schedule is just a nightmare of restriction vectors, and nothing is going to be resolved by that one. Only I lose more CPU time by actually running my reclaiming algorithm in the process. So I have to be careful about this. Then the other parameter you're looking at is what is the ratio of my actual execution time with relation to my worst case execution times. You will be surprised how often in practical real-time systems that ratio is simply 1. Because you're not even trying to be faster. You often have the reflex in hard real-time systems to not program a while loop, but you're actually programming a for loop. Because it makes your verification easier. Because it makes your predictability a lot easier if you know that you're blindly running through these machine instructions all the time anyway. It makes the structure of your program a lot easier. But it also means my actual runtime will simply be exactly always the same, which means it's identical to its worst case time. If you have a hard real-time system of that sort, resource reclaiming is futile because there is no difference between the actual execution time and my worst case times. And the migration attempts, the number of swaps which I have between my CPU lines, I also have to be careful. That could cost me a little bit on top. Basic resource reclaiming, constant complexity, early start, goes with a number of processors, but that's usually irrelevant. And restriction vectors without CPU swapping doesn't cost you much at runtime, but it costs you something at compile time, which is irrelevant because it's compile time, so it doesn't influence actual runtime behavior. But for the actual task migration restriction vector system, you have to add the overhead which comes with actual swapping CPU queues. Okay.
So with these calculating when things will be run at compile time,
Yeah.
if this is a program that intends to just kind of keep running and not terminate, if it's something that intends to run for a year at a time or something like that, it would just have some table of the time to run each of these tasks if they run for very brief periods of time.
Sure.
So is this only for things that intend to run for a short period of time and then finish?
Yeah, you need to have some spare capacity in your schedule, and there has to be a point in the reclaiming. I think this is where you're heading. If I have only my one task, which has to run every half an hour, what's there to be reclaimed? What are you doing with the additional resources? But if you have, for example, a system which if something goes bad, the recovery costs could be immense, and if I have, in case that my system goes a little bit that I have lots of CPU resources which I can throw at the recovery phase, then that's a system which lends itself better to those kind of setups. Okay. If you have, for example, a very complex algorithm to recover from bit errors in my system, that I need to have a lot of CPU power to reconstruct the original state of my system, in case I have enough cosmic radiation that my system gets out of whack and I need to recover from that. Having more CPU time will make your system more robust if you have that available. Just as a strange example how this can happen. Okay. So, and a little bit careful how much this is applicable to hard real-time systems. You have to be cautious. Can you even allow for earlier start times? your example that the point of the system is that the task is running every half an hour, then there is no point starting it earlier because that's the definition of this system. So if you have minimal delays in my task scope, that violates the preconditions for that one. And we should be able to do task migration if you want to do a restriction vector with task migration. That's not necessarily the case in all real-time systems that you can migrate that so easily. And that you're also able to express all dependencies based on that formalism. That's not necessarily the case in practice. There could be more implicit dependencies coming at you. Okay. So actually this is pretty much where I wanted to conclude today. I don't want to push you any further for that. I want to just let the resource reclaiming idea sink in first before we continue on for the next chapters. That makes sense? Okay. Give you an early dinner. Are you guys having dinner before you come here? Sometimes? Okay. So this grumbling noise is not just my imagination, which I'm getting from at this time of day.
Sorry, I wasn't on the allergies. I really like the content. It's just a bad time of day.
I'm not blaming you. This colleague was actually quite shocked when I told him that. A colleague, yeah, because nobody's going to fall asleep in your lectures, right? No, they do.
Well,
What, really?
The most interesting lecture. Like, objectively, I really enjoy the content.
I can see that.
Well, it's not even, I'm just like comfortably.
No, I'm
I just
sorry.
like it. I'd be fast asleep. I'd be doing this one. I'm not asleep.
I'm not making fun of you. I perfectly understand that. It's just when we are, how much sleep are we getting these days? And 7 hours, that's
1 hour every day.
Exactly.
Yeah, good schedule. Yeah.
And it's sitting down in the same posture for more than 30 minutes, and some part of your body will decide, that's a good point. Let's grab this opportunity. And your conscious mind is overriding that constantly, trying to get back to that one. I perfectly understand that. Just
You could do
happens.
SLR.
All right. Thanks. See you Friday.